All right. So last week we talked about slope, and we talked about slope being the traditional sense of slope that we've talked about before, like it's the average rate of change. You can use y2 minus y1 over x2 minus x1. But then we also talked about this idea of instantaneous rate of change. An instantaneous rate of change was when we had those 2 points that were like really close together, okay? And with those 2 points that are really close together, we could estimate the instantaneous rate of change, okay? So this definition right here, we called the instantaneous rate of change, but more specifically, we're gonna see that called a lot as the derivative, okay? And so all we did at the end of class was practice using this algebraic structure, this formula for the derivative, okay? We call it the formal definition of the derivative. And we used that formal definition to find the instantaneous rate of change, okay? And so we had f of x equals x squared, and at the end, our derivative was 2x. And so we're going to sort of skip part B for right now and kind of work through example 2, example 3, and I believe there should be one more, example 4 and 5, okay? All right, now let's get started. So example 2 says find the derivative for the function f of x equals x squared minus 2x using the formal definition of the derivative, okay? And so the first thing I'm going to do is write out that formal definition. So I'm going to say the limit as h approaches 0 of f of x plus h minus f of x all over h. And so what we're going to do is think about what we're going to substitute, okay? And so let's go back to our original function for a moment. Our original function says f of x, and everywhere I see that x, I'm going to square it. So it's going to be x squared minus 2 times x, all right? So that pink dot is where I have to put an x value for this particular function. Now, if I think about writing the f of x plus h part, okay, that means x plus h is going to go everywhere I see the x. So every pink dot that I have in the original will be replaced by x plus h. And so this first line is going to look pretty long. The limit as h approaches 0. Okay. Instead of f of x plus h, I'm going to write x plus h squared minus 2 times x plus h. Okay, so instead of x squared, I have x plus h squared. Instead of 2x, I have 2 times x plus h. Okay, so that's my f of x plus h. Minus, what am I going to put for f of x? X squared minus 2x, good. X squared minus 2x, okay? And so we can see here that these two are pretty similar, except one has an x and the other one has an x plus h everywhere we see the x. And I put that all over 0, okay? Now, if I plug in 0 for h, I get a 0 in the denominator, and that's a problem for us, right? We can't divide by 0. So what we need to do is expand that numerator, make it longer and messier. We're going to FOIL, we're going to distribute, we're going to make sure we distribute those minus signs especially, and we're going to make this look a lot messier. But after we make it messier, it's going to get better. Okay, so let's start with this first term over here, x plus h squared. So that is going to become x squared plus 2xh plus h squared. Okay. Now, what am I going to get when I have this second part over here, the minus 2 parentheses x plus h? How do I simplify that part? 2x minus 2h. Almost. What's the sign in front of the 2x? Minus. Okay, good. So minus 2x minus 2h. Okay. And then there's not much I can do to clean up that second part quite yet. Okay. Now, this next part I'm showing separately because it is the number one place people make a mistake. Okay, you do not have to do this separately, but the number one mistake is this minus sign in the middle here. Folks forget to distribute it. And so we want to make sure that this becomes minus x squared plus 2x. Okay. So our next line, the limit as h approaches 0, we have x squared plus 2xh plus h squared minus 2x minus 2h. And now we have that pink part, minus x squared plus 2x all over h. All right. Now let me pause for a moment and just remind us that these terms all came from the f of x plus h. So those first 5 terms came from f of x plus h. And the last 2 terms come from f of x. Okay, so we still have f of x plus h minus f of x. Now, the beautiful part is at this point, things should start to cancel. Okay, so specifically, we might notice that x squared and x squared cancel. And we might see that negative 2x and 2x cancel. And so we're left with the limit as h approaches 0 of 2xh plus h squared minus 2h all over h. Okay. Now, after things cancel, here's how you know that you are headed in the correct direction. Everything in the numerator, you should be able to factor out an h. Okay. You should be able to factor out an h from the numerator. If you cannot, something went wrong. Go back, double check your signs. Make sure that you FOILed. Salud. Salud. Okay, so make sure that you've done everything correctly. After you cancel, you should be able to factor out an h. Then we have the limit as h approaches 0. When I factor out the h on the top, what do I have left inside the parentheses? (2x plus h minus 2). Perfect. 2x plus h minus 2. Now, the beautiful part about being able to factor out an h that was a problem in the bottom, gone, no more problem. And so what we have now is the limit as h approaches 0 of 2x plus h minus 2. And so what is our last step here? Awesome, plug in 0, and I love Laura being more specific. You plug in a 0 for h, right? Because we have here that h is approaching 0, so this value is now going to go to 0. Now we can try substitution. And so what are we left with? 2x minus 2, okay? And 2x minus 2 is the derivative of x squared minus 2x, okay? So I'll give you a moment to look over this. This one was actually fairly similar to one of the quiz questions that you had. I believe it was question number 5, okay? So if there are any questions, let's maybe take those now. If you have any clarifying questions about number 2. Otherwise, we're going to move ahead to number 3 so that we can take a look at some other structures that come up commonly. We could use, that's a great question. So in the chat, there's a question that says, why do we use the letter H? H is just a letter that represents the distance, like the horizontal distance between 2 points. I don't know how H got picked, but in theory, you could use A or you could use B, like any letter is fine, but typically we see it as an H. Okay. Well, let's take a look at example number 3 then. Okay, so example number 3 looks pretty similar. It says find the derivative for the function of f of x equals the square root of x using the formal definition of the derivative. So Eric, that's a great question. Delta is the same concept, but what we're saying is H is, like I said, it's just the way that folks decided to name it. I think they use delta for some other things. So some people use delta X, but I think some people also use H. All right, but if you see delta X, it'll be the same thing. I have a professor who, when she says the letter H, it comes out H. That's how she says it. So sometimes when I'm saying H now, I think H, but whatever. Okay, so let's take a look at this question. It's asking us to use the formal definition of the derivative. So let's start by writing that down. The limit as H approaches 0 of f of x plus H minus f of x over H. And we know that f of x is the square root of x, okay? And that means that when I try and plug in x plus h, both the x and the h will be underneath the square root. And so we'll get something like this. The limit as h approaches 0 of the square root of x plus h minus the square root of x over h. Okay, so I've got my f of x plus h, and I have my f of x. So if I try plugging in 0 for h, I'm going to encounter a problem because I'll have a 0 in the denominator. So how have we fixed this in the past? How do we handle a situation that has square roots? Right? How do we handle that situation?
Finding the conjugate of it.
Mhm. Exactly. We're going to take a look at using the conjugates. Okay. So I'm going to multiply by a super fancy way of saying 1, but that 1 is really the conjugate over the conjugate. Okay. So that's one of the reasons that I made such a big deal of knowing how to do conjugates when we were looking at limits, because I knew we were going to see that kind of structure again when we got to derivatives. Okay. All right. Now we are going to clean up the top because that's where the conjugate pairs are. So we're going to FOIL out the top, but the bottom, we're going to leave it alone. Okay. So we're just going to write the bottom as h times square root of x plus h plus square root of x. And when I multiply out the top, I notice that I have a square root of x plus h and a square root of x plus h. And that's just going to give me x plus h. Okay. Now the outer and inner terms, those are going to cancel. That's the beauty of the conjugate. And so now I need to just look at the last terms. I have square root of x times square root of x, which gives me minus x. So let me pause here for a moment and let's see if there are any questions about how I got from line 3 to line 4. Okay. So if there are no questions right now, let's move on. So what can I do to clean up the numerator here? Combine the x's, okay? So x minus x, check that out. They're gonna disappear, which is incredibly helpful because now I have an h in the numerator. Oh shoot, I have that h in the denominator too, right? No matter how complicated this gets, I know that you know h divided by h is 1, right? So I can reduce that to be 1. Whew. And so what do we have here? The limit as h approaches 0 of what? Do I have a fraction anymore? Yes, okay. Numerator, love it. The numerator is a 1, right? That was definitely a really important concept here. Then when we reduce, the h's go away, but we also need to think about what's still there, right? There's a 1 in the numerator, and then the only thing left down here is the square root of x plus h plus the square root of x. All right. Perfect. I love it, Graham. Sub in 0 for h. Let's see what we get. And again, we're having h approach 0. So this h, I can plug in a 0. And I have 1 over square root of x plus 0 plus square root of x. which is the same as 1 over square root of x plus square root of x. And what does that give us for the derivative? Let's be really careful with our algebra here. Yeah, 1 over how many square roots do we have in the bottom? 2. 2 square root x. And so 1 over 2 square root of x is the derivative of square root of x. Okay. So let's pause here for a moment. I know there's probably a lot of frantic writing happening. And let's see if there are any questions that are coming up for folks right now.
I had a question about after the conjugates part.
Okay.
So the square roots cancel each other out for like the x plus h, but for the x's, why wouldn't it be 0?
Because what we have there is we're saying negative square root of x times square root of x, which gives you negative x.
Oh, okay.
Is that what you were asking?
Yeah.
Okay.
Thank you.
You're welcome. Okay, so let's see, we got a couple questions in the chat. So if you plug x into f prime or the derivative, it will give you the slope of the line tangent to f of x. Yes, 100%. And that is where we're going by the end of this week. So that we're going to learn some shorter ways of finding derivatives. We'll be able to plug values in. Will tell us the slope of the function at that point. Okay. At what point, okay, so another question in the chat, at what point would you know that you're done? When you cancel out h, as in the first problem, it was the problem with subbing in 0 for h. Yes, so as soon as you get rid of the problem, then go back and try substitution. So it's just like we were doing for limits. We plugged in 0. I was so happy to see people plug 0 in on the exam and like put a frowny face when they realized that it was going to give you an indeterminate form, right? That's the whole problem. But once you substitute or you factor or you use conjugates and you get rid of the problem, then go back and try substitution again. Ah, okay. So I would say the best way to check and see if you're done is just to like plug in 0. If you plug in 0 and it's still a problem, keep going. But if you can plug in 0 and it's not a problem, plug in 0 and move on. Does that make more sense? Okay, cool. All right. Any other questions right now on example 3? If you're not sure also about this conjugate situation, like how we're multiplying and making it so simple in the numerator, that is a kind of question I am 100% happy to answer in office hours, okay? So if you still have that question, 100% valid, but maybe check with me during office hours for that, okay? It does not mean that it's not important or that, wow, I still don't get it. It just means we need to sit down and unpack that a little bit more, okay? All right, I think we're gonna do, we are gonna do number 4, and then we are going to move on from there. Okay, so we're gonna do number 4. I will do number 5 when I post my notes, okay? So you'll be able to see that one. I think that's definitely a little bit more of a stretch kind of problem that I want us to see and kind of think about. But ultimately, where we're going this week is finding shortcuts for some of the work that we're doing. And so I think that might be best to kind of sort of leave that one to go over as you see fit. Okay. So let's take a look at example 4 then. It says find the derivative for the function 9 divided by x using the formal definition of the derivative. And so when we see that formal definition, just like we did with the last 2 examples, we're going to start by writing out that formal definition. And so let's look at our function. Everywhere we see an x, we're gonna plug it in. And so we have like a 9 over x situation. So what is that gonna make my f of x plus h? What is my function when I plug in x plus h going to look like? Nine. Thank you for putting those parentheses there. 9 over x plus h. That is exactly right. 9 over x plus h minus 9 over x. And so we have our x plus h and we have our x. All right. What's the deal with this? What strategy comes to mind when we see a fraction minus a fraction?
Denominator?
Yeah, exactly. We're looking for a common denominator here, okay? So even though this was stuff that we learned in the last chapter, some of these strategies are actually really valuable in other contexts as well. And so let's go ahead and rewrite this. And I think in the example that I did in class, I sort of split this into 2 fractions. Like I had 9 over x plus h minus 9 over x. I'll leave space to make the common denominator. And then I did times 1 over h. So I just brought this denominator out as sort of a separate fraction, just because it was easier to see like 2 fractions side by side rather than a fraction stacked on top of another fraction. I did see some people use this strategy on the exam, so that's awesome if it works for you, and if not, totally fine as well. Okay, so our common denominator here, let's think about what we want to multiply by. First fraction, I'm going to multiply by x over x. What should I multiply that second fraction by?
X plus h over x plus h.
Yeah, exactly. X plus h over x plus h. Okay. So now let's work out that common denominator. We'll end up with 9x over x times x plus h minus 9x plus h over x times x plus h times 1 over h. All right, I've got my common denominators. Now I can turn 2 fractions into 1 fraction. Now I can subtract. And so I'll get, let's see, 9x minus 9x minus 9h over x times x plus h 1 over h. So let me pause here for a moment in case you're writing away. And let's just make sure we've distributed correctly. Let's see if there are any questions about where signs came from or how things got to be a single fraction. So this minus sign between the 9x and the 9h, are we all okay where that came from? Why would it be 9 times x plus h? Like I had one denominator that was x plus h, and then I had another denominator that was x. I didn't have any denominators with a 9. Yeah. Okay. So maybe the one thing I do want to clarify here is this minus sign. We have to distribute that to that plus. And so that's why we end up with 9x minus 9h over here. Okay, that's a really good way to phrase it because the parentheses are around the x plus h. So you're not just distributing that 9, but also that negative sign. Okay, perfect. All right, well, we are at the point in the problem where things should start to go away. Specifically, 9x and 9x make 0. And then we're left with the limit as h approaches 0 of negative 9h over x times x plus h times 1 over h. Now, after we cancel out some things, we should be at a point where the h's go away, meaning that this top h and that bottom h, this one and this one, they reduce. H divided by h gives you 1. So we don't have that anymore. Now, there's so many things we could do here. We could distribute that x into the x plus h. We could split it into, different fractions or whatever we want. There's a lot of things we could do here. But remember that we always want to go back to substitution. So now seems to be a good time to say, let's substitute in 0 everywhere we see an x and see what happens. Because if we can get an answer, then we're good to go. We don't need to do anything else to the expression, okay? Now, when we plug in 0, check out what we get. Negative 9 over x times x plus 0. Correct, Laura. Everywhere we see an h, not an x, because we're saying as h goes to 0, not as x goes to 0. Oh, sorry. I meant to say an h. Okay. Is that 0 in the bottom a problem for us? I think it's fine, right? Because x plus 0 is x. So we really get negative 9 over x squared. And that is our derivative of nine over x. All right. So let me see if there are any questions here about number 4. All right. So if you have questions on these, please come see me during office hours. I'm happy to walk through a problem like this with you at a pace that suits you, to write out as many steps as you feel like would be helpful to see. Okay, these are things that are great for office hours. Okay. Now, example 5, I will put that one up when I post the notes. Okay, so we're not going to go over that one in class, but I think it's a good stretch problem in the sense that it combines fractions and a square root. Okay. I will also go over question number 6, which I think is very, very similar to that quiz question that you saw, as well as example number 2 from today. Okay. The one thing I wanted to point out for example number 6 is this. Okay. We are in this next section going to be learning a lot of new symbols. And sometimes with these new symbols, it's really important that we understand what it's asking. So when we see this dy over dx, okay, oops. The way we say this is dy dx. We don't usually say dy over dx. We say dy dx. But this is the same as saying derivative. Okay, so when we see that dy over dx, that is the same thing as saying derivative. All right. Now there are a few more ways to say derivative. We'll write those out in the 3.3 notes, but I just wanted us to start to notice some of that notation. Okay. All right, so I'm going to stop the recording here.